Hello everyone, Ken here, back with the fourth installment of the Data Science Fundamentals series. In this one I'm talking about regression, particularly simple linear regression and multiple linear regression. I got a lot of feedback on the poll that I posted about what types of videos you guys would like to see, and tutorials were one of the main ones. I thought that regression was a great starting point after the data cleaning, manipulation, and exploration, because it is one of the foundational machine learning or data science techniques that you use in the field. This technique is great because it serves two purposes. One, it shows the exact relationship between our independent variable, otherwise known as a feature, and the dependent variable, otherwise known as the outcome variable or output variable. This interpretability is really important when you're explaining your findings to stakeholders or to other people, because a lot of data science, the really progressive methods, are kind of a black box, and we want to be able to, explain everything that goes into these things, because it's more likely to be used in industry if people can understand it. We also can project new outcomes on new data that we haven't seen with this model, so it is inherently valuable. It's also relatively simple. If you want to follow along, all of the code is in my GitHub repo, which is in the description. The data, which is on Kaggle, the link to it is also there. So in this video, I'm going to show you how to use the ordinary least squares approach. A little example here, we can use a picture. So in any regression, or any linear regression, you're fitting a line to your data. And what you want is a line of best fit. And so in the ordinary least squares, we want a line that minimizes the square distance of each of these points from the line. So we want one that minimizes the aggregate. This penalizes really far off samples, and it helps us fit a line that we believe is most representative. So that's talking about a simple linear model where we're just having one independent and one dependent. When we have a multiple linear regression, we do the same thing, but we plot it on multiple planes. So if we have two independent variables, each of those go into the slope of that line to give us the best fit there. All right, now let's get started with the analysis here. Before we actually run the regression, we need to make sure that the data is of the quality that we want. We also might want to do some feature engineering. We might want to do some manipulation. And I've outlined those steps in the previous data science fundamentals videos. You can also find them on my GitHub, but let's just get started here. So the main packages we use for cleaning, exploration, and manipulation are pandas, numpy, and matplotlib. Again, I'm going to kind of breeze through these steps because you can catch up and follow along with those on the other videos. Next, we're going to read in our actual data, which is this Craigslist vehicles data set. So this is a pretty big file. It's about a little over 1 gigabyte, so it might take a second here. It's important to really understand this data, evaluate how many nulls there are and things like that, because we don't want to use a data set that has too many nulls. So doing that, we can actually see what the columns are. So we have, I think for this use case, let's try and predict what the seller will price the vehicle at. We have year, manufacturer, make, condition, all of these different variables that are relevant. So when we do data.describe, it takes all of the continuous or numeric variables and it tells us some of their descriptive statistics. So we can see that the average price for a car is around, it looks like 10,000, 13,000. The average year is around 2008. And same thing for the odometer, it's around 10,000 miles. So one thing that is useful is we want to drop duplicates. I don't think there are actually any duplicates in this data set, so that might not have been a necessary step, but you really in general don't want to have duplicates in your data. The next thing we want to look at is we want to understand how many null values there are. So this little snippet of code sums up all the null values for each row, and we divide it by the number of rows that there are. So we see URL and price and city, etc. They have, there are no nulls there. Condition and it looks like size have significantly more nulls, and we want to determine what we do with that later. We might not even want to include those columns if there's too many nulls there. For something like condition, it might actually help our model to understand, if they actually didn't put the condition. That could be a negative relationship there. If we wanted to kind of shortcut that step, we can run this line of code here, which would drop all of the columns that had less than 60% of the data. Now let's jump into a little bit of feature engineering. So we have this description field, which is a big string. It has information about the car, and I could do some text processing on that, but I think it makes more sense to say, hey, maybe if the description is longer, people are willing to talk more about the car. That might have an impact on what the price actually is that they set. They might be more attached to it, something along those lines. So what we do is we just take the length of that description and we convert it into basically a numeric variable from this mess of string variable stuff here. I guess you can't really see it because my big old head's in the way, but now you can see it. So now, if I just wanted to do kind of a sanity check, we have 400, looks like 400,000 data points, and there's only 11,000 rows where the description is more than one, with a length of more than one. So that might be concerning. I'm going to evaluate that later in the model to see if that's something we'd actually want to change. One thing we could do there is change it to say, hey, like the description is larger than one, or the description is 1 or less, and that would be a dummy variable instead of an actual continuous variable. So the next thing we want to look at is cylinders. That to me should be a numeric, but it looks like it is a string variable right now. So we see 6 cylinders, 4, 8, 5, 10, other, and 3 cylinders. And to me, I would like to convert this into a numeric. So we do that with this quick lambda function. We replace cylinders, we strip it, and then we convert it into a numeric. So we can look at the value counts again. There we go. Now they're either not a number, numeric, other, etc. And we use this pandas to numeric, and we coerce those values. So now it looks like this. And we have all of these actual float numbers instead. So for our dependent variable, for our price, we want to understand what it looks like if there's any outliers, because outliers can really skew this type of analysis. As we can see, we have some prices that are in like the millions here, and I don't think that anyone is going to buy a car on Craigslist that is that high. So let's look at like what the max price of a car is. So that's looking like, oh my goodness, like $1 billion, 4 billion. Let me do this one. Yeah, so $4 billion. I think that's a little high for the price of any car on the planet. So that's likely someone fat fingered it, or they put the price in wrong. Same thing with the odometer. I sincerely doubt there are too many cars with 1 million miles. So we want to remove everything within a reasonable confidence interval. So we're going to make this new data frame called data outliers, and we're going to remove like the top 0.05% of the price and the bottom 05%, as well as and do the same thing with the odometer. So we get a more normal looking price plot. There you go. We can see, our data is looking a lot more reasonable there. We're looking at, no prices that are in the millions anymore. Same thing here. So what we want to look at next is the distribution of our data. So cylinders, obviously it's a little spotty. Price, it looks like these follow an exponential distribution. Odometer has some serious right skew. Same with text length. These aren't necessarily factors that prevent us from running this regression technique, but it is something that we should know going in about the distribution of our data, because it is not normally distributed. The independent variables and the dependent variables of a regression do not have to be normally distributed in and of themselves, but you'd like the residuals of the outcomes to be normally distributed. The residual is just like the error, so we have a line, and the distance from the line is the residual. And if the residuals are not normally distributed, that means that our line is only representative of a portion of our data, rather than the whole data set. So again, let's look at the null values and start imputing those here or removing them from our data. So we see the year has a very small percentage of nulls, manufacturer has a small percentage of nulls, make has a small percentage. These are ones that have a very small percentage. I personally would just remove them from the data. It makes it easier to work with. We don't have to worry about any area there. So for these, so for example, a manufacturer, make, fuel, transmission, title, status, year, all with relatively low null values, let's actually just remove them from the data set. So we've dropped that subset, in place equals true, so it's removed from the other one. So as you can see, those values are now equal to 0 nulls, which is exactly what we want. I'm going to scroll up a little bit more so you can see that more easily. There we go. All right, so the next thing we want to do is we have a lot of nulls in cylinders, and I think it makes sense to actually impute this information. So we're going to fill it with the mean. Let's actually switch this to median because we can't have half cylinders. So we're just going to, for the null values, assume that that car has the median amount of cylinders there. So now if we run this again, oh, I guess I ran the shape again, we can see that the cylinders, there are no null values. And finally, for a couple of the categorical variables, condition, VIN, drive, type, paint color, we can say that these are actually just not included, or like there isn't a value, and that might actually tell us something useful about the model. So for example, VIN number, we might want to know if the car has a VIN number or does not have a VIN number. That would actually be very telling. People might be significantly less interested price-wise if there is no VIN. So after doing this, we can see that size, latitude, and longitude are the only ones with null value still. I think that size has so many non-values that we shouldn't include it in the model at all. So I'm just going to remove that entirely when we actually run this analysis. I'm also going to do exactly what we said with VIN. Let's just make it a has VIN or a has no VIN, because the individual VIN numbers are going to be pretty useless to us. So for our final data, we want to drop city URL, city size. We're going to drop the description, but we're going to keep in the text length, the latitude, longitude, and image URL. None of these are going to be relevant for us determining the price. And then for one type of analysis, so we're going to use both the sklearn linear regression and the stats models ordinary least squares linear regression. And so for ordinary least squares, you have to add in a constant. They do not do that for you. If you're doing this in sklearn, they do. If you're doing this in R, they add in a constant for you. That's just to figure out where the line actually starts. So right here, we need a constant to figure out what the beta is, B0 is. I also wanted to, instead of doing the year of the car, do the age of the car. So that's just, how old it is. It's effectively going to be the same, but it makes the newest cars equal to 0 and the oldest cars have a higher number. That, to me, it normalizes this data a little bit rather than having it randomly be in the 2000s. So after our final look at our data frame final, we see that we have no null values, which is what we want. One thing before we start the actual regression analysis is we want to understand how the data is actually interrelated. We do not want our independent variables, our features, to be too highly correlated with each other. And this is how we evaluate that with a simple correlation plot. So we want all of our independent variables to be highly correlated with price, but fairly lowly correlated with themselves. So obviously year and age are the same thing. They're converses, so we'd expect this to be 1. But we're only going to be using one of those in the model. Other than that, we see year is positively correlated with price, cylinders is positively correlated with price, text length is positively correlated with price, and odometer and age are the opposite, which is what we'd expect. I don't see too many crazy things. Odometer and year are fairly highly correlated. but it doesn't look overly strong. We just want to make sure, and there's a way to test how correlated these variables are, but we want to make sure nothing stands out, like two things are, super highly correlated over like 0.6 or 7. Okay, finally actually getting into the regression model here. So we're first going to do a simple linear regression with only one variable. We are going to choose the odometer, and we're going to have to import a couple things here. So the first, from sklearn, we're going to import train test split. So when you run almost any model, you want to separate the data into a test case, a train case, and a test case. So you train the model on the train case, you build it, and then you see how well it generalizes to the test case. That's one way of semi-evaluating how it would perform on new data or in the real world. So we're going to just import that. We're going to import the linear regression, which is what you'd expect. We also want to import a couple metrics, and these are how we evaluate a regression model. And then the last thing we're going to import is math, because I like using root mean square error rather than mean squared error. So for our independent or feature, we're going to look at the odometer values. And in order for it to run in sklearn, we have to format the data in a very specific way. So let's look at what that actually looks like. So when we just do it without changing the formatting, it transforms it into a series. When we add values, it turns it into a NumPy array. And then when we actually reshape the data, we get basically a NumPy array that has a larger size rather than just being a series. We do the same thing with our price, which is our dependent variable, and then we can actually work. So now we actually split this into the train and test set. We use a test size of 0.03. So our training set is 70% of the data. Our test set is 30% of the data. And we set the random state. That just lets you replicate the analysis at a later date if you'd like to. So now we have these training and testing set datas. We're gonna fit our linear regression. So the way you use any of the sklearn algorithms is you create this linear regression object, and then you fit your data to that object. After you fit it, you can get a score of that data, or you can predict, or you can do any of these things. So score is going to be r squared in this case. And what r square is it shows the amount of variance that is explained by this linear model. So 0.26 is not overwhelmingly high. That means we explain 26% of the variance in price through the number that is on the odometer. So what we do next is we want to actually predict both the train set and the test set. So we're going to first look at how our model did from a training perspective, like on the data that we actually trained it on. And then we're going to look at how it extrapolates to a test case. So we have this scatter plot and our projections based on that. And so we can see that there is some general relationship between the odometer and the price. However, it doesn't really look like this is that good a fit of a line. There's a lot of variance and noise on either side. We're going to do the same thing with the actual prediction. So y hat test is the prediction of the test set, and we're going to kind of see how that generalizes as well. This is just a visual representation. These look almost identical to me, but we do want to understand a bit more about the actual error associated with these. So there's a couple different ways to evaluate a regression analysis. So the first is with R-square, which we use to evaluate how well the training set actually maps to the line. But we also want to look at a couple different ones. My favorite, actually, we should do this one first. So the first one you generally think about is mean absolute error. So the mean absolute error, it just takes the average of the distance of each of these points from the line. and it takes the absolute value of that because there'd be negative values on this side. So that doesn't particularly skew for values that are very high. They're not as penal as perhaps they should be. So what I like to use is root mean squared error. So mean squared errors, we just take all of the errors and square them. And then if we take the square root of that to get what it actually means in terms of distance from the line. So we see that for this, the mean absolute error is around 6,500 and the root mean squared error is around 8,700. And root mean square error to me is more valuable because it is more penal for these huge outliers. We don't want huge outliers in our data, and to me, we want to minimize this root mean square error. If you don't care that a couple of your values are really high, you could potentially optimize around mean absolute error. But for most cases, again, I think this root mean square error is a better decision criteria metric. Alright, so we're going to do the exact same thing, but using the stats models API OLS regression. I just think this is more useful for the summary information. So again, it's the same thing. We create this OLS object. Here we actually include the data and then we fit it. You can look at all the documentation. I have it for sklearn, the linear regression, and this OLS model in the description below. But what we're going to see here is that you actually have to include the constant in this data set because it's not included for you. That's really the only main difference aside from having this better summary statistics page. There we go. So a couple things to note here. So we have the same thing, R square, adjusted R square. Right now, adjusted R square doesn't mean too much to us. Adjusted R square is relevant when you have multiple different independent variables, because the idea of a good model is it should be as simple as possible if it gives you the same result. So when you add more variables, the adjusted R square actually decreases because you want to maintain that simplicity. The F statistic and the omnibus test, we want them to have a p-value equal to 0. That suggests the model as a whole is significant. If we're looking at skew and kurtosis, those can be represented by the Jark-Barra test. And the Jark-Barra test is related to what I was talking about earlier with the normal distribution of the residuals. So we actually don't want a significant p-value for the Jark-Barra test. That suggests that our distribution is actually not normal. This isn't necessarily a good thing. It doesn't mean we can't use this model, but it means that our method might not be, or our linear, the type of line we're using, might not be a best fit for the data, and it could explain some random variance there. This might mean that we should use a different type of line, a curved line, an exponential regression, or we might not want to use a linear model in general. But for the purpose of this example, we can still continue on with this. The Durbin-Watson test, we want it actually to be right around 2, and this is to evaluate autocorrelation in data. So if you're looking at a time series and the individual data point is related to itself in the future, the Durbin-Watson would be fairly high. We want to eliminate that in our data sets for the most part. Now that I've gotten some of those light explanations out of the way, let's get down to what actually really matters for your model here. So first we're going to look at the p-values of basically the odometer. What we can see here is that means that this variable is significant in explaining the outcome of price. Now we can create the linear coefficients here, and what they mean is that price for this model starts at around $2,000, and for every increased mile on the odometer, we would expect the price to decrease by 0.08. So we can put this into like a linear shape where it would be, the model for this line would be 2.3, so 2, 3, 2, 2, 3, 8 plus, well, I guess it would be minus 0.0864 times miles on odometer. And that would be how we regularly calculate or make predictions on a new vehicle. Alright, so hopefully that was relatively easy to understand. Again, the main things that we really care about are the p-value, the coefficient there. When we build a multiple linear model, there are a couple other things that are relevant to this analysis as well. So let's start with a multiple linear regression using the stats models package here. So what we're going to do is, instead of having just the odometer, we're going to include age, cylinders, and text length. We're going to start just using the continuous variables, but in the next iteration we'll add in the actual categorical variables as well. So our x2 and our y2, for the stats models we don't have to reformat the shape of these like we do for the sklearn model. So that's another easy thing that, you know, why I sometimes prefer this as well, but we do have to remember to keep this constant in. So we have our independent and dependent variables, and now we do our same train test set. And then we can just run this again, and we see different results. So with our previous model, we saw the R-square was 0.26, or it explained 26%. But in this model, we see the R-square explains 43% of the variance. So that's a great improvement. You know, we haven't quite doubled our results, but it's come pretty close. And so again, we want to look at our p-value here, and we see that all of these values are significant in this explanation. The constant, now it looks like, with all these other variables included, we want to start the car price at around $9,000. And then we subtract for age $394 for each year, 0.0651 dollars, or 7 cents for each additional mile on the odometer, and then for each cylinder we want to add around $2,000. And then finally, for text length, for each additional word we want to include, we want to increase this 54 cents. This is pretty menial, it's pretty small, so I wouldn't get too excited about that, but it does suggest that this is still significant here. And we are better at projecting with all of these variables included. So when we have a multiple, we're doing multiple linear regression, one thing that we do not want to have is these variables being extremely highly correlated with each other. That is generally a bad practice that can cause a lot of problems with how this model is built. And so we want to evaluate that using the VIF statistic. So that stands for the variance of inflation factor. And in constant, we're not too concerned with, obviously, because we included it's included in every model. But we want to make sure the VIF statistic for all of these is generally under 4. If it is not under 4, we would actually want to remove one of these, or which, whatever is highly correlated with each one of these, because that will confound the analysis here. So if you have two variables that are, have a large VIF statistic, I would experiment with removing one and the other, and then see which one, if you keep it in, has the highest R-squared or adjusted R-squared. Alright, so the third model that we're actually going to do is we're going to include a couple categorical variables as well. So, we're going to keep age, odometer, we also want to keep text length, and then in cylinders, condition, fuel, and VIN and type. And so, as you can see, I use this pandas get dummies here, and what that does So we can't actually interpret a categorical variable in a multiple linear regression. We have to make them into what are known as dummy variables. So for each category, it has its own column, and in that column we evaluate, hey, is it of that type or not? So let's just explain that through a quick example. So this is x3, and as you can see, we have our normal variables, but then we have condition excellent. So it's 1 if it's an excellent. Condition fair, it's 1 if it's fair, all the way down the line. And then same thing for fuel. So if it's diesel, it'll have a 1 there. If it's gas, it'll have a 1. If it's electric, it'll have a 1. And obviously, you can't have more than one of these having a 1 at a time if you've got the dummy variables this way. And so technically, you only need 1 less than the total number of categories for your number of dummy variables, because if none of them are included, that means it is of the last type of case. So now that we have those included, we can actually run this model again. Okay, so now I run these 2 variables, and we can actually train this new model with all of these things included. So we have now 33 different independent variables, and still just the 1 dependent variable. So we fit it, and then we look at the summary here, and this is pretty interesting. So if we go up, we're looking for p-values that are less than 0.05, and so it looks like, so if the type is not applicable, that is not relevant for analysis. If the type is other, that is not relevant for analysis. And if the fuel is gas, which is interesting, maybe that's because it's so common that is not relevant to our analysis as well. So we would actually remove those from our regression equation, or we would run the model again without those in it. But again, I'm not going to go through all of these, but let's see if there's anything really interesting. So age is relevant as we expected, so is odometer. Cylinder is relevant as well. We would expect that the condition, if the condition is excellent, the price would be higher. Probably the highest if it's like new, so that is continuous with what we thought. This is interesting. If the condition is not applicable, maybe that those are being sold by a dealership, so they'd be a little bit higher. I'm not sure. Condition new is obviously what we would expect to be the highest. So we also see that diesel cars generally go for more. Electric cars, oddly enough, go for less. And let's see here. Hybrids go for more. If they have a VIN, they're more valuable than if they have no VIN, which I think is interesting. That they still, this is not a negative value. I'd probably have to look more into that specific data point. Yeah, but the types, again, are interesting. You'd expect minivans to be less. Off-road vehicles are slightly more. Pickups, trucks, SUVs, convertibles are highly priced, which these are all things that are in line with what we would expect them to be. All right, so after evaluating that, we want to look at if this error has improved from what we previously saw. So let's take a look at the root mean square error here and what it was above. And so with our new model, we see that on the generalized data set, we do a lot better. We're looking at 2,000 almost, 2,000-ish dollars closer on this account, which I think is a great improvement in the model. That's represented by the R squared as well. We can see here that the R squared represents almost 57.5% of the variance. We'd probably like that to be higher, but I think when people are setting the price of their own cars, they might be slightly irrational. And there's also a lot of kind of wonky things like where the price will be 1 and people will be asking for, like, give us a price or your best offer, etc. One thing that I think this could probably be more valuable to predict is the actual selling price of the car if they had that data included. Alright, finally we want to do just a quick scatter plot to see how well this data is represented. So it looks like there's a fairly clear linear relationship between our projected and our actual data. One thing that it looks like might be a better fit is if we were to use an exponential line or something like that. And I think that that's a video I'll make in the future about using exponential or logarithmic linear regression. So the final thing that I want to do is to show you how to actually validate this data, or how this would look in the real world. So we built this regression model, but we haven't introduced any randomness to test it. We don't know if this train test split is representative, so we want to run that a couple times. So we're going to use a 5-fold cross-validation to do that. And what happens is the data is just split into 5 different sets, and the same model and testing process goes on to each one of those. So in theory, I actually don't need to do the train test split here because it does it in the actual thing. But we're going to use this, we're going to include text. Oops. All right. So in theory, we don't actually have to use the training or even really evaluate this model on these, because this cross-val score will do it for us. So it'll train the actual model. Let's actually even remove these, just so we don't have to worry about it. Oh, actually no. Let's keep those, and then do another like that, where we don't have that. Because we want to see what the model looks like when it's fit in general, and also how it generalizes. So what happens here is we get our normal score, so 5.75 R-square, which is what we had before, but we now want to test this on different samples of the data. So we're going to do this 5-fold cross-validation, where again we do the exact same thing, but 5 different times with 5 different data sets all within our data. And now we want to see what the actual scores would be. If we take an average of these, this would generally be representative. And so we saw before that our root mean square error was around 6,700. That checks out here. It looks like it might, on average, actually be just slightly lower than that, which is good. That means that we're comfortable with the results of our model, and we could actually start using it. Generally, again, there's a large error associated with this. We're talking $6,000, which could be more than the price of a car. But this model is a good start for actually evaluating this question. And hopefully with cleaner data, with with more information, this could continue to improve. As usual, thank you so much for watching. I hope this video was valuable to you. Please leave any comments or questions that you'd have related to this data, the methodology, etc. in the comment section below. And good luck on your data science journey.